So this is the third question based on bending stress. So here in the question, a rectangular beam section 300 mm wide and 500 mm deep is simply supported over a span of 4 meter and it carries a UDL of 10 kilonewton per meter. Find the maximum bending stress induced and also draw bending stress distribution diagram. So here in the question it says that it's a rectangular beam. So it's a rectangular beam of 300 mm width and 500 mm deep, and it is a simply supported beam. So it's a simply supported beam and over a span of the span is 4 meter and it carries a UDL of 10 kilonewton. It says that it carries a UDL of 10 kilonewton per meter, and find the maximum. Here what we have to find is the maximum bending stress. Now, and also we have to draw a bending stress distribution diagram. Okay, so now here we know that bending stress equation is m by I is equal to sigma b upon y. So this is the main formula of bending stress. So now here for a simply supported beam, the first thing we have to find the moment. So for a simply supported beam, the moment can be determined from this formula, that is WL square by 8. So here load is given, this load is given and the span is 4 meter. Load is nothing but 10 into L is 4, the whole square divided by 8. So here we'll be getting the answer about 20 kilonewton meter. So now we have this value with us. Now second is to find for the I is nothing but the moment of inertia. So moment of inertia for a rectangular section is BD cube by 12. So we have all the values with us. B is nothing but 300 into D is 500 cube by 12. So here our answer is 3.125 into 10 to the power 9 mm 4. So here now we have to find this bending stress. So next is we have to find for the y value. Y is nothing but, say, this is the rectangular section of B is equal to 300 and D is equal to 500 mm, and this is the neutral axis. So here D is known to us, depth, and Y is nothing but the distance from neutral axis to the top layer, that is Y, that is Y. So Y is equal to D by 2. So Y can be determined by D by 2. So D is already known to us, that is 500 upon 2 is equal to 250 mm. So now we know that the bending equation formula, that is m by I is equal to sigma b upon y. So we have to shift this y value that side, then our equation will become m by I into y. So just we need to put all the values here, that is m was m was this one 20 kilonewton meter. So 20 into 10 to the power 6, we have to convert in Newton mm, divided by I value is 3.125 into 10 to the power 9 into y is 250. So we'll be getting the bending stress value is 1.6 Newton per mm square. So this is the answer for bending stress. Now next in the question what it says that we have to draw the bending stress distribution diagram. So for a simply supported beam, okay, for simply supported beam and for a rectangular section, this is our bending stress diagram, where this is sigma c. Sigma c is nothing but the stress in compression, and here sigma t is stress in tension, and here the distance from neutral axis to this part is yc. C stands for the compression, and this distance is for the yt. T stands for the tension. So why the distribution diagram is like that, I'll explain you. Okay, so this question is based on simply supported beam. So it's a simply supported beam. So what will happen here? The load is acting. So our deformed shape of this beam will be like this. Okay, like this. So here what will happen? This upper layer, the upper layer of the beam will face the compression, and this down layer will face the tension. That's why our bending stress diagram will be, this is the end, this is the neutral axis of the beam, okay, and it will remain constant. So this is the neutral axis of the beam, and upper part will face the compression. So this part will face the compression, and this down part will face the tension. That is sigma t and sigma c, and this distance, this upper part is compression, facing the compression, so the distance will be yc, and this distance will be for the yt. So we can say that in for simply supported beam for a rectangular section, yc is equal to yt. Okay, thank you.